All right, we're back. We're on page 6 of notes 12 of Calc AB. We're talking about definite integrals and all geometric stuff really. And we're going to do kind of an application type problem right now, just to get a sense of how these work, because in the long run, it's mostly going to be applications. So let's see. Graph of the derivative v prime of t. So this is v prime of t. V prime of t. I wonder what the units are. Of the volume v of t of water in a cooler is shown below. The volume is measured in liters. Time is measured in minutes. So this, I guess, liters per minute, and then this would be minutes. I think it's good to do that. I don't always do it. I probably should label things up. It's harder to make mistakes with units when you do that, but what are you gonna do? At t equals 7 minutes, there are 20 liters of water. So that's going to be important. So this is a graph of the derivative of the volume. And that's why, like on this graph at t equals 7, v prime of 7 is 0. It's not going to give you 20. 20 is on the graph of v of t, which we don't have. So everything we do is going to be based on v prime. And what time intervals is the volume of water in the cooler increasing? How do you know? Well, this is a graph of v prime. So v, the amount of water, will be increasing anytime v prime is positive. So here are all those. So let's say v of t is increasing on, I'm going to go straight from 2.5 to 10. Straight at exactly 7, it's not increasing or decreasing. It's like it's flat for a second. But on an interval, I'm going to say from 2.5 to 10. So on 2.5 to 10, because, but now I need to say v prime of t is greater than or equal to 0 on that interval. So that's our justification. Seems good. I mean, if you don't like that, break it up. Do 2.5 to 7 and then 7 to 10. And then you can just say v prime is greater than 0. And maybe you're more comfortable with that. I think that this is an okay answer, so I'm going to go with it. On the volume of water in the cooler at t equals 10 minutes. All right, so what do we know? We know that at t equals 7 minutes, there's 20 liters. Oh, sorry. At t equals 7, there's 20 liters. And then we also know that we add some, right? Because we can find, if I do the integral of v prime of t dt, then that's going to be liters per minute times minutes. That's liters. That's like my displacement, like how much water has been displaced in that amount of time in liters. So what I'm going to do is I'm going to say that the amount of water at 10 is going to be the amount of water at 7. So v of 10 is going to be v of 7, the amount we start with, plus the displacement from 7 to 10 of v prime of t dt, right? So we're looking at, so not the, it's the displacement from 7 to 10 of v of t. It's the definite integral from 7 to 10 of v prime of t dt. So this is going to be 20, which was given, that's what we started with, plus, let's do geometry. This is 1/2 3 times 1. So 1/2 of 3, 1.5. So I'm going to do that. 1.5, 21.5 liters. That's how much is in there at 10. Find the volume of water in the cooler at t equals 5. All right, so let's think this through. I want to know at 5. So 5 is like here. So if I were to find this is, what is this? 2 by 2, so 4, but half of it, so 2. So this is 2 liters. But that's the displacement from 5 to 7. And at 7, there's 20. So if you gained 2 between 5 and 7, and at 7 there's 20, you must have started with 18. So that's like a logical way to do it. What I'm going to do is kind of like, I'm going to use this idea of displacement again. So the idea is if I do the integral from 5 to 7 of v prime of t dt, that's the displacement of v of t. So that's v of 7 minus v of 5. Like that's got to be what it is, right? Thinking in terms of displacement. So then if I solve this for v of 5, v of 5 should be equal to, so what I'm basically doing is adding this to both sides and subtracting this. So it's going to be v of 7 minus the integral from 5 to 7 of v prime of t dt. So you can rearrange these things. It's all based on displacements. Think about displacements. So this will be 20 minus, I think we said 2, so 18 liters. All right, so that's like a big idea. It's important, and you want to like make sure you understand that because it comes up a lot. At what times is the volume of the water? At what times is the volume of water in the cooler a relative maximum or a relative minimum? How do you know? So we just want to know the times at which it's a relative max or relative min. So if v prime changes from negative to positive, which it does here, then v goes from decreasing to increasing. This is a relative minimum. This is a relative maximum because v prime goes from positive to negative. This is like a false start. So I'm going to say that at 2.5, v prime changes negative to positive, so that's a relative minimum. So at t equals 2.5, v prime of t changes negative to positive. Therefore, v of t has relative minimum at t equals 2.5. And then at, I think the other one is, I think it was 10, but I'm not sure. Yeah, t equals 10, v prime changes from positive to negative, so that's a relative maximum. So t equals 10, v prime of t changes positive to negative. Therefore, v of t has a relative max. Sorry, I was just reading. At t equals 10. Put in autopilot, you know? At what times could the volume of water in the cooler be an absolute maximum or minimum? Candidates test, right? So v of t, volume has got to be continuous. So v of t, first of all, I'm just saying volume's got to be continuous. But also, we know the derivative exists everywhere. And if the derivative exists everywhere, that means it's differentiable everywhere, between 0 and 12 at least. And differentiability implies continuity. So v of t is definitely continuous. So v of t is continuous. Oh, you're not a marker. It's continuous. Therefore, absolute max min at endpoint or critical point. So therefore, it's at t equals 0. I'm going to list them. T equals 2.5. Don't read, t equals 7 is a critical point. It's where the derivative is 0. It's not a max or a min, but it is a critical point. Or t equals, nope, t equals, you just don't need the or. T equals 10 or t equals 12. So there are a lot of candidates. And so that's why it's called the candidates test, is because they're all candidates. Could happen at this value, this value, this value, this value, this value. So, and I guess I should say by candidates test here. So instead of this period, we're going to say by candidates test. Candidates test. And then in the next problem, we're going to actually like do the candidates test. So we'll make a table. And then, so what we need to do though is we're going to use that idea of displacement like a million times. So let's say t, and then v of t. So there's going to be 0 at 2.5, at 7. So at 7, we know it's 20. That was given. At 10 and at 12. I think we already figured out 10. Yeah, 10 was 21.5. So 21.5. Okay, so let's think. I think the next easiest one is 12, because to figure out 12, I can just do where I was at 10, 21.5, plus the integral from 10 to 12 of v prime of t dt, right? So let's figure out that integral. From 10 to 12, you lose 2. So that's minus 2. 21.5 minus 2 is going to be 19.5. Ooh, what are you doing? 19.5. Now we got to go backwards. So I'm going to say that v of 2.5 is going to be v of 7 minus the integral from 2.5 to 7 of v prime of t dt. So I'm doing minus because what I'm essentially saying is that the displacement of v, right, the integral from 2.5 to 7 of v prime of t dt is the displacement. That should be v of 7 minus v of 2.5, and then I rearranged it. So that's where this is coming from. It's the same idea as when we found this. Same exact idea. We're going backwards. So I need to find the integral from 2.5 to 7 and then subtract it. So 2.5 to 7, is that annoying? I think it is annoying. All right, so what are we gonna do here? I'm going to cut you here. Oh my gosh, what are we doing? Here, I mean, this is 0.5, this is 0.25. Like you could calculate that, but like just look at it, right? Like create this grid, which like this will bite you every once in a while because it's not, like I'm assuming that it works perfectly. It's 1/4 of that. And then what are we doing? This is 3, and then 3 by 1, but then 1/2, 1.5. All right, what are you? You are 0.5, 1.5, so that's 2, 5, 5.25. So, and we're subtracting that. So 5.25. So we got to do 20 minus, good grief, zoom out. Okay, 20 minus 5.25. 20 minus 5 is 15, it's 14.75. Okay, the next one, v of 0. So I'm going to say v of 0. I'm going to keep doing it. I'm going to say it's v of 2.5 minus the integral from 0 to 2.5 of v prime of t dt. So the correct answer to this would combine the answer to part E and part F. Like that would be the perfect answer. I'm like breaking it up the way it told me to break it up, basically. I need the integral from 0 to 2.5. Hopefully not hard. So 2, and then another 2, so 4, and then another point, so 4.25. 4.25, and I have to subtract that. So that's annoying. 4.25. 14.75 minus 4.25 is 10.5, I think. 10.5. If you add 4.25, you get 14.75. If you add 5.25, you get 20, 21. Okay, so I think those are the values, I'm pretty sure. So the biggest value and the smallest value are the absolute maximum. So the absolute minimum is 10.5, which occurs at 0. And then the absolute, is that right? Was that negative? That was negative. I'm subtracting a negative. What was it in my brain that told me that that was wrong? The thing that told me it was wrong was I was like, oh yeah, there's a relative minimum here. If there's a relative minimum here, then how could the value I'm getting here be smaller, right? Like without some kind of sign change in the derivative. So that was incorrect. So now, do I remember what the numbers were? 4.25. I have to add 4.25. That takes me to 19. Good save, maybe, potentially. All right, so the smallest value is this. And then the biggest value is this. Could have been an endpoint. It wasn't. So I'm going to say, therefore, and I think I got these right, but I don't know. I hope I did. Usually in class, there's people checking for me. So absolute min is, what was that? 14.75 liters at t equals 2.5 minutes. And then the absolute max is, what is it? 21.5 liters at t equals, I guess, 10 minutes. So these both happened at critical points, could have been at endpoints, nothing, because it's a candidate test, you know, anything could have happened there. This is a really important idea. This is a very common type of question. This notion of using displacement will get more formalized as we go, but like, that's how you do it. You're either where you are and you're going forward, or you're where you are and you're subtracting what you did to get there. So it's a very straightforward idea, I think. But anyway, good problem. I'm gonna stop this here, come back in the next one and do some more. So I'll see you there.